In this third presentation on data science for Shale, we'll basically be putting the things that we discussed in session 1 and session 2 together. So now we're dealing both with the case where we have covariate information and also where we have spatial variation in the production due to changes in the geology. So this part of the work has not really been published in journal papers, but can be found on as a PhD thesis of my former PhD student, Oki Grucic. And so I do think that by now that we should be able to download that PDF for that thesis from the Energy Resources Engineering website where all the PhD dissertations are listed. So we will again be working with the same data set by Anadarko. So we have a number of wells that have been drilled. And on the right-hand side, we see the gas rates and oil rates for these various wells. And at the same time, we have recorded a number of parameters, such as the completion parameters, fracturing parameters, as well as the geological parameters that have been provided to us. So the nature of the data science problem is now the full problem, which is basically we have different decline rates, gas, oil, water. So we have a multivariate functions we need to predict, and these are also spatially varying. Also, these functions are informed by multiple covariates. These are the geological and completion parameters, and as you noticed in the previous slide, the observations are noisy. So let's first look at how we would tackle the problem without covariates, and this refers back to the presentation on Trees and Kriging. So typically in geostatistics, we would write, let me get my pointer. We would write something we'd like to predict at some location where we don't have observation as some mean function plus some residual function. And so this mean function is treated as deterministic but unknown, and the residual function is stochastic. And so we calculate for this part, the residual part, we calculate variograms or trace variograms. In the previous presentation, we've seen that we have used basically a drift term that's function of location, where the weights given to those are functions themselves. So these are the functions of time. And so this takes the problem into a functional regression problem instead of just a classical regression problem. Let's now look at the prediction framework with covariates. Basically, we have still the same model. We will be writing our production decline in several wells, in several kinds, such as gas and oil, as a mean function plus some residual function. However, now we'll add the covariates into the mix. So the covariates essentially are geological and completion parameters, as well as the spatial location of where things are occurring. So now instead of having Q a function of T and S, we get Q as a function of T and X. So X0 would be the covariates observed at the location to be predicted, and so on. And so we have again this residual term. So now we get a different drift term, an augmented drift term, where in addition to having previously just the S, we also have essentially the various covariates that will be trying to where the drift term will be depending on. So we'll get many more of these beta functions simply because we have many parameters. On the other side, the trace variography, as we've seen before, remains the same within this estimation framework. The question now is how we'll be modeling this drift term as it looks to be more complicated as before. For that, we will be relying on regression trees. So regression trees are quite, I've introduced that method in previous presentations, so I'll just briefly go over it. So in regression trees, we're not trying to fit a parametric function to some data. Instead, what we're trying to do is to approximate something by piecewise interpolation. So we have a space, say, where we have two parameters. It could be, say, porosity, permeability, and we have some response we'd like to predict, say, oil, cumulative oil at 10 years. So we have observations, or either from Monte Carlo or through some data set that's provided to us. So in regression trees, what we do is, as I mentioned before, is instead of fitting a parametric function, we basically fit the division of the space. And we fit this division of the space in a particular fashion, and we'll talk about that in a bit. If we indeed have that, then in each region, we'll just average the values and use that as a prediction of the model. So basically what you get then is these are now the averages. What you get is a piecewise discontinuous function through these various regions. So that can all be organized in a tree. For example, here we notice that we split first on x, so that would be x being less than 7.5. And then again, we split on x, I believe, would be 8.5, and so on through this tree. So we can, that's why we call it a tree, in the sense that the topography that's created in this fashion by this hierarchical splitting leads to this representation by a tree. Okay, how do we build regression trees? Well, we have to, as I stated before, we have to determine where and when to split. And so that by itself is a methodology that I will not go into detail. The only thing that is relevant is that we have to decide to split and where to split. And so once we have that decision, imagine that it would be here, then we can calculate a cost function that relates to how much the split actually helps you in fitting the data. So if I have no split, then of course my estimator is the same everywhere. It would be the mean. However, if I have two regions, I calculate a mean in this region and a mean in that region. What I hope is, of course, that my cost will go down, my least square difference will go down, and I get a better fit. And so the idea is to split at a location where you have the best fit. So there's a split quality. So we have the cost with the whole region, and then the cost, the reduction of the cost by the cost in the left and the right region, and that would then be that split quality. Okay, and so the cost, as I said, is a square deviation from the mean in that particular region, so from the model. So different outputs will then lead to different cost functions, and so we move that into a different definition of cost functions, and we move that around, and we can then keep on splitting, etc., etc. The splitting can be performed on any kind of input, so you can decide between splitting on scalars, category, and functions, and so that holds a nice feature of the regression trees, as it is very difficult to regress function scalars and categories to some other function scalar and category. So many of you probably have used regression trees in the past, and they are quite powerful methods. But what if what you'd like to predict is a function? Would you then build a regression tree for each time step in that function? Or what shall we do? And so that we have to develop new methods for functional regression trees. So imagine now indeed that I have two parameters, and those and I have a function. The function is of these two parameters as well as of time. So these would be the covariates, let's say, and this is the function of time. So obviously, if I make a split, what's going to happen is that I will have two groups of functions. So if I make, say, a split of x1, I will get two groups of functions. So now I need to calculate a different cost function. So previously my cost function was just the least square difference, and so now our cost function will be an integration of a difference over time. So with the integral over time of that difference between my observations and the model, which is the mean in that group. So again, I can work with left and right, split quality and costs, and do it that way. So that's one way around it. Another way around it is to look at the same problem. So we make a split, we calculate the functions, and then what we do essentially is calculate the distances between these functions. So instead of looking at a time behavior, but integrals over time, we're going to do something a bit more general, where essentially we are calculating the differences between these two groups. So that gives you a distance matrix. So if I have, for example, 100 curves, then this would be a 100 by 100 matrix. And then I can do multidimensional scaling. And so in that multidimensional scaling plot, what I get is two groups. So two groups, each representing different functions, and of course, each representing different parameters associated with those functions. So what I can now do is I can look at the group in its totality and calculate, for example, what would be the medoid distance between points in the totality of the group versus the medoid distance in the red group and the medoid distance in the left group. So if these would be the same, essentially, then I would have no reduction. However, if these would start to be very different from the total, then I will get a reduction in cost, and that would be an effective split. So this reminds us a little bit about the methods of sensitivity analysis that we've mentioned before, which is, for example, distance-based generalized sensitivity analysis. Remember, in that case, we also made two groups, and we looked at the parameter values in those two groups. And that allowed us to essentially calculate sensitivity of a parameter value. If the parameter value in this group, the x1, say, in this group, is different from its histogram is very different from the x1 in this group, then I have sensitivity. So we're sort of using the same kind of idea here, but now we apply it to the cost functions, and we're using the medoid instead of the histogram as a representation of what is different. The nice thing about this is that we can extend that to multiple functions. So imagine that now we don't have just oil rates, but we also have gas rates. So in that case, I will again calculate these distances, and I would have distances related to oil and related to gas, and we'll add those distances up. And so we get exactly the same method as before. Once we have an MDS plot, we would calculate the medoids in different groups. Okay, so now we can start to put things together. So we have seen in previous presentation the method of trace Kriging, Kriging by interpolating production data from other production data. However, we did not deal with covariates. We've seen a presentation where we only deal with covariates and try to predict production from those covariates, but not deal with the spatial interpolation problem. And so here we're trying to leverage both, right? So there's an amount of information that is provided in the covariates in terms of what the production would be. And there's also an amount of information that's provided in the spatial correlation that exists between the production. So depending on the kind of prediction problem that you have, one will be more important than the other, but it's important to develop a framework that does both. So yeah, so we have, again, this very noisy observations in this data set, and so we'll have to deal with that. Another problem we'll have to, the first issue that I've mentioned many times before is that functional data analysis, by which you will express the decline or the function as a linear combinational basis function with some smoothing to it, allows you to somewhat reduces this kind of noisy observation. There is, however, another problem that is occurring in reality that we need to deal with. And that is that the situation that occurs in functional data analysis is often not as nice as it would be according to theory. Obviously, the reality is often different from theory. And one of the issues that we have to deal with is that the production lengths are not all the same. Some wells have been in production for some amount of time, others for a much longer amount of time. And so we get basically functions over different lengths. And so functional data analysis in itself does require that all production or all functions are of the same length. So how do we deal with that? Well, for example, in our case, we notice clearly that there are wells that are have over 150 days up to 2,000 days of production, and some wells probably have production that is much shorter, say to 250 days. So the way to do that is some kind of an ad hoc curve completion. This is what we will be doing. So the first step there is to choose some time where we have enough observations, say over several, maybe 100 observations, or maybe even less. Maybe that depends a little bit on the situation. But we have a sufficient amount of observation where we can start doing some modeling. So obviously, if you take 750, then there's only very few wells that have that amount of production. So we'll look at that subset. So for example, we know truncation here is around 5,600. We smooth that subset. We do our traditional FDA. And so then the question, then we do functional principal component analysis, which gives us the functional principal components for that. So now what do we do with a well that has only 300 days of production? Well, what we'd like to do is we say, okay, well, let's truncate these functional principal components at 300 and let's calculate the scores that we will give based on these functions by a simple regression. So what we're doing here is to calculate or estimate from this data set what would be the functional principal component scores. Why do we do this? Well, the reason why we do this is because we have the function. So extrapolation will then basically mean that we're relying on the functional principal component functions, so the principal component functions after that particular time in order to allow us to do this extrapolation given the estimates that we have of the principal component scores at the earlier time. So we do that and then we reconstruct. And so when we reconstruct, we get this nice extrapolation. So this is now our new, let's say, observation that can be added to this data set for estimation. Okay, so we'll deal with two cases. First, we'll look at just oil and gas separately, and then afterwards we deal with both oil and gas, so we can estimate both of them. And so just to remind you that indeed, in that case, we'll be looking at distances between oil curves and water curves separately. I think this should be water, not gas. Okay, so here is a fitted multivariate tree. So when we're in a tree, what we're looking at is it seems like the first split is on something to do with the stimulation and of the laterals. So that will be the first one. And the second one seems to be on the geologic x. That means the x coordinate of where the well has been drilled, and so on and so on. So we can look at groups of curves. So we can look up groups of curves based on split. The blue group would be this group. So you notice that there are a couple of outlier curves over here, and otherwise everything is split in this other group. And this is both for water, I think, gas, sorry, and oil. So we can keep looking further down. So here we look now at three groups. This is the black group, the blue group, and the red group. And so you get more and more differentiation as you go down in the tree. So here we look at this black versus this. It seems like this contains some of the interesting behavior where you have first an increase and then a decrease, and so on. So in previous presentations, we mentioned also sensitivity analysis or parameter importance, variable importance. And so we can do that now based on these trees. We can calculate the single variate tree important and the multivariate tree important. It does seem that these seem to overlap considerably. We don't get a huge difference between single and multivariate tree. Okay, so now you can start to do prediction. Namely predict essentially what decline rate would be in a series of new locations given existing production existing locations as well as covariate information. So in order to evaluate that a little bit, we split our data set in two parts. So we have some wells where we're going to do fitting and some wells where we're doing testing, and we're creating various models to do so. So we had a single variate model with a tree. Actually, we use a random forest tree. I'm not going to go into the details of that. A single variate on oil and then a multivariate on both. And here's the way we summate this. We create a measure of evaluation, which is the sum of squared errors in functions. Okay, so we have now fitted our trees, and so we have basically the mean variation of our predictor, which is that decline rate as it varies over space, as well as function of these covariates, the completion and geological parameters. So once we have the mean, we can calculate the variogram of the residual, and so here we're looking at, for example, the variogram calculated after doing. Let me put on my pointer. Here we see, for example, if I have a single variate tree, and this is then the variogram of the residual variogram of the gas rate that I have in this particular field. And so you can start fitting variograms. So then I can start doing predictions. So essentially uncertainty quantification. So here we have a prediction related to oil and a prediction related to gas with a single variate tree. So here we notice this is the actual, the dots are the actual production, and this is the smoothed variation of that. So this is the one that's withheld in the test set. And so the green is the one that's obtained by our method. You say, well, where does the uncertainty quantification here come from? That comes from the using a random forest instead of a tree. And again, I have not talked much about how that works, and I refer to the PhD dissertation that I mentioned in the beginning. But what you see is that you get a sort of a nice covering of the actual test set. So on the right, we get the gas rate, and here we notice a set of green curves and a set of red curves. So the green curve is if we only use the random forest or the trees as a predictor, and we ignore spatial variation. So basically, we ignore the variogram calculations that were done in the previous slide. So that's basically like doing regression without accounting for spatial correlation among the production curves. And so we notice that if we actually account for the spatial correlation in addition to that, then we get a better estimate in general. Although the improvement is not that great. I would say here that the tree actually does already quite a good prediction, and the spatial correlation in the variogram due to the variogram between production data doesn't really add much to that. So knowing or stating what are the completion and geological parameters is sort of overriding that. Now, in reality, of course, we could expect that we would not know essentially perfectly these geological parameters, and so we have an additional uncertainty, and then perhaps the spatial correlation between the decline curves will become more important. Okay, that brings us to the end of this rather broad overview. So there are many details there that probably you're wondering how things work, and again, I refer to the PhD dissertation where you'll find all the details, as well as the codes essentially that were listed in the front of the presentation. But I think you'll have appreciated the main message here, which is that we are decomposing this prediction problem into two things, which is a classical regression problem, which many of you are familiar with, I believe, but also a spatial interpolation problem. Basically, we have two things here, that we have information that is provided by the spatial correlation in these production declines, and as well as its relation to covariates at those specific locations. And so our approach taken was here to look at the regression problems to trees, which and extend it to functional trees, simply because trees allow for that flexibility. So we're not trying to predict the scalar, but we're trying to predict something more complicated. And in the spatial interpolation, I refer to the trace Kriging methods that we had been handling before. The other issue, of course, when you deal with real data is dealing with the fact that they're noisy, that there's an amount of processing or pre-processing, pre-selection that goes on into determining what eventually the data set is, and so that's really specific to the problem, and I didn't talk too much about that at all. They also, I think, a nice contribution here on how to complete incomplete data sets using functional principal component analysis. So that's it. I'd like to thank Anadarko for providing us the data. And if you happen to be a company or an entity that has this kind of information, I'd be happy to have a conversation with you. I think these methods need some more testing, and more data leads to more testing. So that would be great. Well, thank you for listening.